our lesson for today, I'll just walk you through what I mean by high dimensional images by telling you about how they are captured. Okay? So marami, but we will limit ourselves in this course to three. And what are these three? Ay, wait. Press down. Yan. The first is multi and hyperspectral imaging. So these are all digital images. We're not talking about analog images here. So of course, when you have an analog or digital image, you have a camera, the cross section of a digital or rather DSLR camera, single lens reflex. You have your optomechanical part, which are the lens barrel with all the mechanics and the lenses there. And of course, your optoelectronics here. So you have over here is your imaging sensor. You have circuitry to convert the image into to digitize the analog image, and then of course some processing internally. Okay. So the sensor can typically is either for commercial cameras. Typically, it's either charge coupled device or complementary metal oxide, but they serve as the retina of a camera. Each of these cells here are the light sensitive elements that capture light coming from the lens. So if an image is formed on the surface of the sensor, then those are saved. They are converted to electrical energy, which is then passed on to some buffers. And then their positions are known because of the way these information or the charges from here are transferred to um, uh, um, the last end. Usually it's a bucket brigade way of sending this digital information. So from this pixel, papass yung information down there and then bucket brigade all the way here. All right? Ganun din sa CMOS. Okay? Think of this as the retina of your sensor or of your camera. Now, these sensors are actually sensitive to range of visible light and slightly up to near infrared. Okay, so depending on what kind of sensor, this graph tells you the spectral sensitivity, meaning this is 400 is roughly blue and around almost 700 is red. So this is the Roy G. Biv wavelengths. And over here are the infrared, okay? And this graph here is the relative spectral response, meaning that sensor, in this particular, this is a graph for a CCD, it's highly sensitive to yellow, green to orangish light, okay? And it's also sensitive to a bit of infrared, okay? And usually these cameras come with an infrared cutoff filter such that our images would not look like a surveillance camera na pang night vision. Without this IR cutoff filter, infrared light from surfaces will come in. All right, so usually it's just the visible light is let through by the IR cutoff filter. There are many other sensors available, and these are some of the different spectral sensitivities. So essentially, if just you have this sensor, the same CMOS or the CCD, well, actually, when you take an image with that, it's just a black and white image. All right. So how is color produced? Because when you say multispectral or hyperspectral, that means different spectra are recorded or different wavelengths are recorded. But with the CCD itself or with the CMOS itself, actually it's a summation of all of these taken all together. No? So essentially, without any intervention, it's just a black and white camera. So this black and white camera can be made into a color camera by putting an array of filters, colored filters on top of each of these picture elements. Okay, so for example, This is known as a Bayer filter, mosaic. It's a set of filters with alternating red, green, blue filters matching the pixel locations. You see, it exploits our eyes being only sensitive to 3, not really very being sensitive, but it exploits the trichromaticity of our eyesight, meaning if you combine 3 primary lights in different intensities, we can perceive a color, right? So because we just need 3 primary lights, color cameras usually just come with 3 filters on top of their sensors, and the intensities coming through the blue, the green, the red filter are combined or put in different channels, and therefore when overlaid, they give a sensation of color sa image. Actually, that's not the only kind of filter. Other filters come like so, the CMYG, and then there's this RGB white, meaning this is just a clear through glass, and the rest are filter mosaics. So there are many types of combinations of these, and they will produce a color image just from a black and white sensor. Now, there's also another way, and actually ito yung ginagawa sa mga satellites, and multispectral satellites actually use this technique. Instead of having a filter, the image, or rather the light coming from the scene, is sent through a prism, and this prism splits the light from the scene into 3 parts. Okay, so it replicates the image into 3, and each of these 3 destinations, they each have a CCD, and in front of each CCD there is a filter, just like this. So there's a prism, it splits the incoming light into 3 locations, and these are the sensors, the CCD sensors, and on top of them there is a single color filter. Like this is green, this is certainly red, this is blue. Now, in Diwata 2, there is a multispectral camera there, and what is there are 4 sensors. So not only RGB, but also there's another prism, okay, and another sensor, but on top of it is an infrared filter. Okay, I have seen some extreme kinds of payloads as well, different cameras for satellites as well. I found something having 17, I think, 17 sensors like this. Sabi ko, pagdating ata sa dulo, konti na lang yung ilaw. But yeah, it can happen that you can have several sensors, and each sensor will have its own filter. The advantage there is the image is sharp, because there's no need to interpolate the values of the pixels in between filters. So as you can see, here's the difference between a single CCD with a Bayer filter and a 3 CCD, each having its own filter. Okay. So this is the case of what is known as a multispectral imaging, because the multispectral there comes from the fact that each of these filters lets in only a narrow portion of the visible spectrum. Okay. Now, when you talk about hyperspectral imaging, you let in everything, the whole rainbow. This is the diagram for our hyperspectral camera that we are developing in the optical lab. So technically, you're looking at the field. It's called a push broom scanner in a way, because here what you see is only a line of the scene. You're only looking at a line of the scene. So the scene, for example, is captured by a lens. There's a slit between this lens and the imaging spectrometer. Actually, here in this imaging spectrometer, there is a single line slit like this, no? And you only see, if this is your scene, no, you only see through the slit just a line of the scene. So if you have a satellite or a drone flying over a field or a scene, no, essentially it's only seeing as a line of the image, but because of its motion, you scan through and you can see, you can capture several lines of the scene and form the scene, the whole scene as you fly over the field. It's Nickname push broom kasi pag titignan mo yung sweep nitong ano na to, nitong line na to na tinitingnan niya, and you look at the rays coming from it, para nga siyang walis. And since the satellite moves like this, it's like you're sweeping. That's why it's a push broom scanner, sweeping the scene. Okay. So after the light passes through the slit, the scene from the field passes, the light from the field or the object passes through the slit. It goes through a dispersing element. It can be a grating, a diffraction grating. Di ba alam natin pag may line of light passing through the diffraction grating, it splits the light into its rainbow colors. And these rainbow colors are saved in CCD, right? Or impinges sa CCD. And therefore, essentially, one line of light produces one slice of a hyperspectral image. Here's an example. So this colored chart, pag ito yung slit, nandito yung slit, after going through the imaging spectrometer, the diffraction grating and the prism inside the imaging spectrometer, this is what it sees. No? Okay. So the hyperspectral image, when you sweep through the whole scene, what you get then is a hyperspectral cube. Okay. And depending on the axis that you're looking, so the XY axis here is a spatial axis. Okay. While this vertical axis here is the wavelength axis. You can slice the image in whatever plane you want. For example, you can slice it in the along a wavelength, and what you see is a monochromatic image telling you how the bright parts would tell you that, okay, at that wavelength, that object or that point of the object is reflecting this color very well or very strongly. Okay, you can also slice it lambda versus x. So you have a spectrum of a line along the x-axis of the scene. Or you can also slice it along lambda versus y. You can have a spectrum of a line along the y-axis of the scene. So here it is in action. So as you can see here, this is the chart, the color chart, and we have a hyperspectral camera on top, and we have a scanner here, and it's going through. So you can see what's happening in the screen of the laptop, or at least here you can see this is the interpretation of the image captured by the CCD. So take this axis as the visible spectrum axis, and this is what is going through the slit. Itong axis na to, okay? Ito yung nadadaanan niya na part nung color chart. That's why nakikita nyo, di ba, may parang grids yung color chart. So may mga itim-itim dito na lines because yun yung lines dito sa chart na to. Okay? So mababa yung spectrum na because they're black. So you can see those bright spots there. So if you see it bright here, ibig sabihin it's passing through a green patch. Okay? All right. So that's how you see it. So that's how hyperspectral imaging works. And we actually have look forward that we have face-to-face para makita niyo yung setup dun sa lab na paglaruan natin. All right, let's go to the next one. It's video. So digital video. But ever wonder how movies in the past were made? Well, just like analog images, no? Yun, may film and you take photos dati. Ewan ko kung naabutan nyo pa yon. I feel so old, but naabutan nyo ba yung may negatives? Tapos i-develop yung negatives. Kung hindi, I feel really old. Sa video, ganun din. Nung gumagawa ng mga old films dati, ganun din. Capture lang ng video, ng picture on a negative, scene per scene. Tapos the images are played back on a screen. So these are just still images, no? Played back in rapid succession, and it gives you an impression of motion. So, ganun din ang digital video capture, very similar to analog or to a single image capture. this is usually the diagram for the electronics or the system diagram for a digital camera. So here you have your optics. This is your CCD or CMOS. Okay, and then out comes voltages from or current from this scene or charges, and this is the heart of it. This is the analog front end. This is analog to digital converter, timer, combined into one, and then what comes out of the analog front end is the digitized version of the analog image. So essentially, this is the analog to digital converter and all other processes needed to control camera. It goes through a DSP. It can be digital signal processing or DIP chip for image processing. There could be some compression, etc. And then, of course, all of these some timings. For example, when you have you have a shutter, when you capture, exposure, etc. So there's timing circuitry as well. And the output is a processed digital image or video. Okay, so this is the heart of it. The reason why we can do a digital video capture and even at very high speeds is because of technology or advances in these analog front ends or these analog to digital converters. I got a snapshot of this because I had a look at what are the phones. Imagine that back in my day, we were wondering if we can afford a high-speed camera for our video biometric experiments because we want to capture movement of athletes in slow-mo. But you know the slow-mo guys in YouTube, di ba? Mahal-mahal nung kanilang mga cameras. But now, commercial cell phones, I was surprised to see that, it can go up to 1920 frames per second. Okay, so if you take a look at this website, it tells you what are the best phones for slow-mo capture. Okay, our phones right now, most of the phones right now can go 240 frames per second. But I was surprised that there is one that can go more than 1,000 frames per second. This is good enough for video biomechanics initial study or reaction of athletes to stimuli. Okay, so have a look at this website. There's a list of those high-speed smartphone cameras already available. You see, because it's high speed, you need a storage device that can also capture data at high speeds. So, well, this is your SD card. If you examine your SD card, it has a label that tells you about the class or the speed class or how fast it can save images. But again, remember the video is just several images in succession, no? So, ito na yung tinatawag na video speed class. This is the latest because we can do 8K na, di ba? From 4K, we can now do 8K video. So, look at the price. It's 10,000 nearly. And so if you examine your SD card, it has several different speed classes, and this table tells you what kind of video it can store. Okay, and the frame, or rather the data writing reading rate that it can do. Okay, write speed. Write speed. Okay, as you can see here. Okay? Wala pa nito nung nag coral capture kami. But yeah, it's fast. I mean, technology is going by very fast. So that's how you get digital video. You need also capture media to store all these images, aside from, of course, having a fast analog front end and fast media to store images coming out of the processor. So lastly, there's 3D, no? 3D image, high dimensional. Why? Because image is technically 2D. Video. So imagine your class. If you think about it, class, 2D ang black and white image. 2D nga ba? if you think of the grayscale of each pixel, the 3D na yon, di ba? Okay? So pag video naman, imagine mo kahit black and white na video, that's already 4D. The fourth dimension being time. So paano kung color? O di 2D, tapos meron pang 3, tapos meron pang time. O di 5D na yun. Sorry, 6 space is in 2 dimensions, and then color is in 3, and time is another dimension. That's already 6 dimensions. Imagine nyo pa to, in space, X, Y, Z. Okay? In color pa. Tapos in video pa. Ilang dimensions na yung kaya nating i-visualize, di ba? The real 3D is tomography. Tomography is yung idea ng tomography is you take a slice of the image, so you also see what's inside the volume. So in images, picture element is called the pixel. In 3D, the picture element are called voxels or volume pixels. Okay. So in tomography, so you have, for example, computed tomography scans or CT scans or magnetic resonance imaging, MRI, and even for non-medical use naman, ground penetrating radar. So what they do is they get a slice of the image and then you build it up, no? Right? Because it scans actually in 2D, and then if you move the scanner, then you can get the next slice, and then you can build it up, and you can stack them and display them in a volume viewer like so. Okay, because different tissues will reflect differently or absorb differently. You can isolate different tissues or like for example here, skeletal system, you can isolate that based on the intensity of their reflection or absorbance. Okay, this is a nice link explaining how MRI works. Okay, but this is the real 3D. In this course, we will do what is known as 2.5D or just the surface, because if you're just using a digital camera, we can only image what is on the surface. You can't scan through or do X-ray on the image. So it's just 2.5D. But well, technically they also call this 3D, but or rather vernacularly they also call this 3D, but technically it's just 2.5D. It's nicknamed 2.5D because you don't see the insides of the volume or the object. Now, just like our eyes just like our setup, no, we have two eyes, no. And with those two eyes, we can estimate how far or near objects are from us. In surface 3D or 2.5D, well, from now on, let's just call it 3D, okay? In estimating, or rather in computing 3D imagery, ito yung minimum requirement. Just with two views, we can estimate depth or range. Depth or range, essentially it means yung how far is each point on this image from the scene or from the observer. Pwede yun. That's why it's called depth or range, no? And there are many techniques for estimating surface 3D. For example, in this image, it's shape from shadows. Here, you have, say, a fixed camera, a single camera, but your light source moves. As you can see, different location of the light source shows different shadows. And the model of the brightness of a surface, depending on its surface normal, no, and the light source direction, okay, from a model of how the surface normal reflects light, given the direction of the camera and the direction of the light source, allows us, if you take images, several images, the unknown surface normal can be determined. Again, doing surface 2.5D requires that we get the surface normal of the object we're trying to get the shape of. So the surface normal, di ba, NX, NY, NZ yun. 3 unknowns yun. No? Okay? You can estimate them from multiple views of the same scene taken by a single camera, but from different shadows, or rather having different shadows. We can flip this. We can have a single light source, and we just move the camera. And therefore, we see different aspects of the scene. But here, in this case, this is called shape from shadow, because we can reconstruct the surface shape from just one camera. But essentially, kung isipin mo, multiple scenes na to of the object, different scenes of the object. Okay, shape from shadow. We'll learn how to do that. There's also shape from stereo, meaning, remember, you need 2 views. You can have a single camera, but you move the camera, and therefore you can get a different view of the scene. And from there, you can estimate the location, XYZ location of each point on the scene. So that's a structure from motion, because single camera, just move around the system, or just move around the scene. Technically, from one step to another, you can already estimate some depths of the points. So if you want to estimate several more depths from points in the image, you take several more video or several more images. So here, there are many commercial software na that we can use to do stereometry. The most popular is Agisoft Metashape. Okay, you can try it for free for, I think, for 14 days, and it's very nice, very useful. And let's just go through. And here you can reconstruct the point cloud of the scene, and then you can overlay the pixel colors from the scene. You can interpolate the meshes between these points. And eventually, if we zoom in, rather move, then we can reconstruct the scene already in 3D. Okay. All right. And lastly, there's shape from structured illumination. So what I'm showing here is what the technique known as phase shift profilometry. Remember, imagine if you have a projector and you have a pattern like this. If you project it on a cylinder, the shape of the cylinder will distort those straight lines and will form like this, di ba? Now, if you have these these lines, no, shifted. Sorry, what's happening? Shifted by phase shift, or rather moved by a certain shift. What will happen is you will have different images for different phase shifts of that pattern. You can actually calculate the phase map of ano yung nangyari dito sa ano na to, sa pattern na to, and it's related to the height of the object. Essentially the phase difference, or rather the phase difference is proportional to the depth or the height of the image using this phase shift profilometry technique. Of course, we'll learn how to do that, but essentially, once you get the phase map, you can unwrap that and you can reconstruct the cylinder just like this. Okay, so we will learn all these techniques actually there. So those are just a taste of some of the high dimensional images that I'd like you to learn how to process. Okay, I'll stop share here. I think this is the last slide. Yeah, this is the last slide. Okay, any questions? Okay, so kung wala, by the way, some of you have been my students before. So yung mga hindi ko pa naging students, welcome. This is Maricor Soriano. Glad you can join. Again, you can use highly recommend MATLAB because of its ease of displaying 3D images, and the fact that anyway we have a license. All right, but there's nothing keeping you from using your favorite programming language. Okay, that's it for today. Next meeting, a first exercise or our first report. I'll give you the activity for our first report. No questions? If none, then let's call it a night, and I'll see you next meeting. Wait, hello ma'am, where can we see the recorded sessions? I post the recorded sessions in my YouTube account. I make it public, okay? So I edited a bit to remove the uhs and ums, okay, to shorten it a bit. And then I post it on my YouTube channel, okay? I'll share the YouTube channel once I post it. Okay. No other questions? If none, so let's call it a night. I'll see you next meeting. Okay? Bye.
Thank you, ma'am. Bye, ma'am.
Thank you
Bye.
po.
Thank you,
Bye, ma'am.
ma'am. Happy weekend po.
Same.